We're live now. As usual, if anyone online wants to post a question, make sure that you're getting things as you should. Good sound, good video quality. Let us know. Should be good though. All right, we're getting into hypothesis testing today, which is the thing that I think many people associate with statistics. This is the essence of answering a question with a yes/no answer, and it's an interesting topic. We're getting into there. We have lots of ground to cover today, and there's many papers will report results like you're going to see today, and there's a lot of controversy over such results. Great, thank you, Eddie and Marcella. So I will relate this back to confidence intervals. These are closely related things in a way. Then we'll cover hypothesis testing both for a population mean and proportion, and cover general things about hypothesis testing, including writing down your null and alternative hypotheses, doing the actual test manually or interpreting it from your software, getting the p-value, and some general stuff about power analysis. And of course, type 1 and type 2 error. But just to review the last class on confidence intervals, remember we constructed those to help provide when we want to estimate a population mean, or it does extend to other things like proportions or any sort of aggregate property of a population, the confidence interval gives us a range in which we have a certain estimated level of confidence that the true population value lies in that interval. So there's a point estimate and a margin of error that includes this confidence interval. And that level of confidence, the common one being the 95% confidence interval, but they can be constructed for any level of confidence, tells us how frequently, if we were to take a bunch of samples, how frequently those the interval estimated from those samples would contain the true value. So remembering the terminology, the margin of error was that the width, or half of the width of that confidence interval. It was the amount above and below the mean that we were confident with the given degree of confidence that the true population mean lies. And for the 95% confidence interval, it was plus or minus 1.96 standard errors, 1.96 being the value of z above which there's 2.5% of the probability in a standard normal and below which. And we can use this either when we have a large sample or we know the standard deviation from the population and we don't have to estimate it from the sample. If either of those things are not the case, but as long as the population of the continuous variable that we're measuring is normally distributed, then we'll use a t-distribution, but we're not going to get that today. I'm just going to keep mentioning it, and then we'll get to it after next week's exam. The confidence intervals that we constructed are really nice in that they tell you about the plausible range of values of something, the range in which we're 95% confident that the true mean lies. So then why do hypothesis testing? The difference with hypothesis testing is it allows us to answer a yes/no question. It turns out in some cases we can do that with the confidence intervals anyways, but there are other cases where you can only do that with a hypothesis test. There are lots of cases where we're interested in answering a yes/no question. For example, does a treatment have a measurable effect on the treatment group compared to a control group? Or do cases who suffer from a disease differ in some attribute from controls in a case control study? Or do, in an observational cross-sectional study, do individuals with some condition differ than individuals without that condition on some other attribute of theirs? So these are all cases where you might start out your public health research with a question. Do smoking or do hypertensive smoking men have the same mean cholesterol levels as non-smoking men with normal blood pressure, for example? Or does intermittent screening and treatment for malaria improve the health and education of school children in a certain area? Or does it make no difference? So these are all cases where there's a yes/no question that we want an answer to. And this latter example is one that I just kind of did a undirected search for recent articles in PubMed and pulled this one up just because it's a good example of something where the statistics themselves for this cluster randomized trial are something that's beyond what we're going to cover in this course, but you can still understand the results of this abstract based on what you're learning in Intro Biostat. So this was a research group that wanted to look at school children receiving this intermittent screening and treatment for malaria as part of a public health intervention compared to those who were not receiving it. Now, a cluster randomized trial differs from an ordinary randomized trial in that in an ordinary randomized trial, you would go and recruit individuals, and then you would assign people to the treatment group or the control group. So you would assign one person to receive the intermittent screening and treatment for malaria, and then another person not to receive it. In some cases, it's not practical to do that, such as in this study, they're applying the intervention on the level of whole schools. It's not really practical just to do this one individual at a time. So what they did was take a whole bunch of schools and randomly assign some schools to receive this intervention and other ones not to. And then they wanted to compare the children with and without the treatment for a couple of things. What were those things? Let's see. So, no impact of malaria intervention was observed for prevalence of anemia at either 12 or 24 months. So they're interested in anemia at 12 or 24 months. And educational achievement. So those are in arithmetic scores and spelling scores. So there is one outcome that is something that you measure in the blood, and another outcome that is educational treatment. There's actually two of each of those outcomes. So we'll get back to this a little bit more, but I just wanted to present it up front here just as a kind of a motivating example. And I did put this article in Blackboard as well, in case any of you are interested in it. Any questions so far? All right. So in constructing a hypothesis test where we want a yes/no answer, the yes and the no, we're going to think about them in terms of random variables and in terms of sampling distributions. And there are two possibilities here. One is that if we're comparing groups, or if we're comparing a group to some known thing, one possibility is that we have the usual distribution that is the same in, say, the treatment and the control, or the same in our one sample compared to something known about the population in the past. The other alternative is that it's different. And this is the basic logic of hypothesis testing. By way of little example of what we're doing here, if we take and grab a handful of beans and see that very few of them are white, and they came from, and we look at a larger bag of beans and see that most of them are white, then we can say that probably those beans didn't come from that bag, right? Doesn't mean it's impossible that they did, but if you have a bag of like 95% white beans, and in this little handful, only 10% of what we see are white beans, then it's probably from a different bag. And in that case, we would probably take option number 2. There you go. Yeah.
Could possibly be, I mean, this might be a worst case scenario, maybe just by chance that maybe it was 10% too, or just making a best guess saying that it wasn't from that bag.
Yeah, that's an excellent point. That it could happen by chance that you just didn't get very many white beans in this handful. If you did that over and over and over again, sometimes you're going to get a really unrepresentative handful, or one that doesn't look at anything at all like the composition in the big bag. And that's what the p-value and the type 1 error that we're going to calculate estimate the probability of that happening. Because yes, that can always happen when you're taking a random sample. So another analogy, this one's used in your book too. It's a popular analogy, which is the courtroom trial, where we consider the defendant to be not guilty until proven guilty. And so in the absence of evidence, you assume that the defendant is not guilty. That would be the null hypothesis. So in the language of the previous slide, you assume that there's no difference in your treatment or your group of interest compared to the usual in the absence of evidence. That's the null hypothesis. It's called the null hypothesis because it means there's no difference. It's the usual, it's the same as the past, and in the absence of compelling evidence, that is the hypothesis that we're going to accept. So then the prosecutor, or maybe the statistician, public health practitioner, goes out and does an experiment, does a study, does an analysis to try to prove the guilt of the defendant, or to prove that this intervention makes a difference, and that is the alternative hypothesis or guilt that they're trying to prove. And you only accept that alternative hypothesis if there's enough evidence that the null hypothesis is quite unlikely. So in the analogy of the courtroom trial, defendant being not guilty is the null hypothesis, and being proven guilty, that's the alternative hypothesis. And so this little table here is a useful table that you're going to have to know in the context of your studies. So there are two possibilities for the truth. That is, that your null hypothesis H0 is either true or it's not true, and the alternative hypothesis is true. So if H0 is true and we accept that null hypothesis, that is, we acquit a not guilty person, we've made a correct decision. And also, if the defendant is guilty and we convict them, that's also a right decision. But there are two types of errors that we can make. So the first one, where the null hypothesis was true, but we reject it anyways, so that means that we're convicting a guilty person. That's a type 1 error. And the other type of error is where actually the alternative was true, the defendant's guilty, but we failed to convict them. That is a type 2 error. And I'll talk lots more about type 1 and type 2 error because those are key concepts for you to understand from today. Both to understand what they are, how they relate to each other, how you control them, and what your probability is of making those types of errors. So back in this example, the intermittent screening and treatment for malaria, if they failed to reject the null hypothesis here, they say that the treatment is not effective. If it actually were effective and they just didn't collect enough evidence, what type of error is that? 2. Yeah, very good. So confidence intervals are related to hypothesis testing, and this is easy to see in the context of the one sample hypothesis test, where we give an interval for the true mean, and or we can think of that in terms of values of z. So for the 95% confidence interval, we went plus or minus a z of 1.96 standard errors. So in the confidence interval, we took the mean plus or minus the amount of z needed to get an area of 0.95, and that's the confidence interval. In the hypothesis test, we would calculate a value of z instead of using 1.96 and calculate the probability of getting that value of z for a sample by chance. So under the null hypothesis here, if I'm assuming here that the null hypothesis would be it's a value of z equals 0. So whatever the population mean is, we take, so if what was the example with serum cholesterol level before, where the normal population mean is 200, and we get a sample where the mean is 210. So the confidence interval approach would be to construct a confidence interval around that 210, and if it contains the null or population regular value of 200, then we don't reject. Does that part make sense? How you would decide whether or not to reject your null hypothesis from a confidence interval? Yep. We know the true mean for the null hypothesis. So the example would be the average serum cholesterol level in the general population is 200. Now we're looking at a group who have been, who have been eating some kind of food. And we want to test our hypothesis. Our null hypothesis will be that their serum cholesterol level is the same as the general population. And the alternative hypothesis would be that it's different. So it's not so much that you know the truth, it's that you assume that there's no difference under the null hypothesis. Yep. Right. If the hypothesized mean under the null hypothesis is not in your confidence interval, then you would reject that null hypothesis. And if you're doing it by a hypothesis test, you go about it a little bit differently. Rather than building that interval and seeing whether it contains your hypothesized value under the null hypothesis, you calculate a value of z and then calculate the probability using a z table of getting that value of z or something more extreme. So it's a slightly different way of going about it. But for the one sample z tests, so for the one sample confidence interval or z test that we'll call it today, they're equivalent. You'll get the same. You'll come to the same conclusions whichever way you do it. Yep. Yep. Right. So on this slide and what we're calculating today, we're talking about one sample compared to just a population mean. In the Kenya example, that's actually, they're doing a two sample test because they're comparing a sample of subjects receiving a control or no intervention to another sample that are receiving the treatment because they don't have the true educational achievements or the true anemia rates for the entire population. So you're getting them both from a sample. And yeah, still in both cases, the null hypothesis is a lack of difference. So in the Kenya example, the null hypothesis would be that the spelling grades are identical whether or not you receive malaria treatment. All right, so this alpha, the 0.05, so if we set alpha to 0.05, then under each tail of the standard normal distribution above 1.96 and below minus 1.96 has 0.025 of the area under that distribution. This alpha is the type 1 error rate. So that's the probability that you grab a handful of beans or a sample of people whose mean is so different from the population that you exceed this critical value just by chance, even if there actually is no difference. Yes?
In this case, you're setting the alpha to 0.05 because you want to first satisfy the 95% confidence interval, right?
Yeah, so by setting an alpha of 0.05, which is equivalent to a 95% confidence interval, it's setting your probability of making a mistake either by constructing a confidence interval that doesn't contain the true mean or of incorrectly rejecting your null hypothesis at 5%. So, and in this case, so with this hypothesis test, as with the confidence interval, we're using the standard error. So we're not using just the standard deviation. We're calculating the standard error. Okay, that's general. Let's go through it very explicitly now. And I think this 5-step program is very helpful to thinking through your hypothesis test, laying it all out, and doing it correctly. So here they are. I'm going to go through them one at a time. So the first step is to formulate your null and alternative hypothesis. And this is very important. And you should actually write it down. What are your null and your alternative hypotheses, so that when you make a decision in the end, you will know what it means. And always the null hypothesis must include there being no difference. We will also cover one-sided tests where it can also include some differences, but it must include there being no difference. So, yes. Yeah, an example. All the way to the first step. Oh yeah. We'll do an example. Yeah. So I'll go through these and then I have an example in here. So the null hypothesis is the one that says there's no difference, and the alternative hypothesis is the one that says there is a difference. And in general, if the sample that we take is not too different from what we expect under the distribution of the null hypothesis, then we'll accept the null hypothesis. But if we see a sample that's very different from what we expect, that you would only see on rare occasions if you took a lot of samples, then we'll reject the null hypothesis and accept the alternative hypothesis. We have formal ways of writing these down, which you should get used to. I'll probably ask you to write some of these down on the exam. And they depend on what type of test you're doing, but in the case of a one sample test, and this is a so-called two-sided test, this is what the null and alternative hypotheses look like. The null hypothesis is that the population mean of our study population is identical to the mean in the population of our null distribution. And the alternative hypothesis is just that they are not equal. Does anyone want to guess why I would call this two-sided? Yes. No, there are always two results in a hypothesis test, true or false, yes or no. Even with one-sided tests, there are two results. Any other guesses? Here's a hint. Look at the alternative hypothesis. How many ways are there that mu could be different than mu0? They could be not equal.
That would be one way.
What's the one way?
Just mu is not equal to zero.
Well, okay, so we're talking here about blood pressure here, say, where in the general population it's 211 milligrams of mercury. And there's the answer from Emily Wolf. So there's two ways that in our population of interest, our study population, that it could be not 211. It could be more or it could be less. And that's why it's called a two-sided test. Thank you, Emily. So this right here is an example of how to write your null and your alternative hypotheses. Way to go, Emily. So the features of these equations, the null hypothesis includes the equal. I've put it in terms of the problem. It's that the mean blood pressure of smoking males, our target population, is equal to, and I've put the actual values, 211 milligrams per 100 mLs. That doesn't sound right, does it? Per 100 mLs. What is that? That's cholesterol, isn't it? That's not blood pressure. Blood pressure would just be millimeters of mercury. Anyways, doesn't matter. You can tell I'm not a doctor. Or a phlebotomist. And then under the alternative, it's the same thing, just that it's not equal. So I've put the numbers and the units. And if when you go to write down your null and alternative hypothesis for a question, this is how you should write them for a two-sided. This is a one-sample, two-sided test. Anyone know why this is a one? So we know why it's two-sided. You know why it's one sample? How you can tell this is a one-sample test, not a two-sample test, for example? Trying to find out yes or no for one particular aspect. We're pretty well always going to do that with hypothesis testing. There's going to be a null hypothesis and an alternative hypothesis, and we're going to get a yes or no answer. But for a one sample test, there's a particular, you can tell from the way this looks whether this is a one sample or a two sample test. Yes? We're going to use mu in any case. Mu is a population mean. Yeah.
Because I don't know if it's going off the topic, but maybe that the smoking male is just one, I don't say the word cluster, but one section that you took of a population.
Yep. Yeah, you're on the right track there. So we're looking at smoking males. We don't have a comparison group here. So this mu is the mean, I think it's actually cholesterol level, of smoking males. So we're taking a sample of smoking males as to be representative of that target population of smoking males. So that's just one sample. We're not taking two samples, say smoking males and non-smoking males. If it were a two-sample test, the hypothesis, and Emily's got another one right. Good job. Because we're comparing one, well, not quite. So just blood pressure, yes, but it's just blood pressure of smoking males to a known value, 211. So there's one sample compared to 211. That's why it's a one sample test. So let's put it another way. If you wanted to address this question, how would you design an experiment to do it? What would your study look like in this case? Yep.
Well, you wouldn't be randomizing people into two different groups.
Nope, not randomizing people into two groups. Yeah, you would identify smoking males. You would take a sample of smoking males. That's your study population. So you just need one sample. That's why this is a one sample test. And then we're comparing it to this known normal value of 211 milligrams per 100 milliliters. Is everyone clear on that now? All right, and of course, if this were a two sample test, say we were going to compare smoking males to non-smoking males, but we didn't have this true value of 211 from the population, we were just going to compare it through our study, then you would need a sample of smoking males and a sample of non-smoking males, and that would be a 2-sample test. And the null hypothesis would be different. There'd be no 211. It would just be that the mu of the one population is equal to the mean of the other population without actual numbers in the hypotheses. Yes?
So in the one sample, you're comparing smoking males to the known, the true value of the general population at large.
Yeah, that's the one sample test where we're comparing the mean cholesterol level of smoking males to the mean in the general population.
And
to a known mean.
well, how is that known then? Like, how is it different than comparing the mean of smoking males to the mean of non-smoking?
Because, so it's known because presumably we're getting this 211 from some enormous study where it was measured in 1 million people or 100,000 people, and there's very little error on this 211. So we can treat that as a fixed value without variability or without uncertainty in it, whereas from our sample, which is going to involve maybe 30 people or 100 people, there's going to be some more important sampling variability.
Or the sample set is smaller than that bigger general population.
Yeah, so I mean, we always assume that we're drawing from a very large population, but the key thing in the one sample test is that this mean that we are comparing to did not come from a sample, because whenever it comes from a sample, there's that sampling distribution, you know, there's variability in the means that we get. But in a one sample test, we assume that that value from our null hypothesis is gotten from so many people that there's really no important amount of uncertainty in it, that it's just exactly 211. So we have one sample in which there's variability in the mean because it's just a small, you know, finite sample anyways, whereas in the value in the null hypothesis, there's no uncertainty in it. That's why it's one sample. Anyone think of another example of a one sample hypothesis test? How about something where we have our population is everybody who all residents of New York. We know the mean income from the most recent census, and we want to test a hypothesis that, I don't know, students at Hunter have a mean income that's different from the population as a whole. Is that a one sample or a two sample test? It's a one sample test, exactly.
So the two sample tests are always like, couldn't we have an enormous amount of data for people that are smoking males or non-smoking males? Like, are you just assuming that the data that you're working with for two sample is much smaller?
So with a two sample test, you could have very unbalanced groups. You could have one sample for which you only have 10 people and another one where you have data for 5,000 people. In that extreme kind of case, your conclusion is going to be the same whether you did a 1 sample or a 2 sample test, because there's so little uncertainty in the mean of that large group compared to the mean of the small group that it's really only uncertainty in the mean of the small group that your uncertainty is coming from. So if you calculate your standard error of the mean on your 5,000, it's going to be very, very small, right? So it would be an interesting exercise, and maybe I should have you do it for. We don't.
Like, my question is, with the 2 sample test, like, well, you said, you know, we have this really large population size, so we can pretty much say that this is the true value for, you know, people, males in general.
Yeah.
But what if you had like a really large population that you knew what the average was of smoking males and non-smoking males? My question is. So
what if you had really large samples of both smoking males and
like,
non-smoking males?
Like that, like be a known true value amount.
So remember, everything we're doing has to do with samples. So if you actually have data for everyone in the population of smoking males and non-smoking males, you don't have to do a hypothesis test or a confidence interval. You can just say how different they are because you have all of the data that exists.
Gotcha. So this is just with smaller samples that you.
Yeah, it's because when you take some small subset from the population, you'll get different results depending on that sample that you take. And that's what all of this is about, that sampling variation.
Okay, great. Thank you.
You're welcome. And yes, that was the Hunter College students was another example of a 1 sample test. So these equations tell you what kind of test this is. It is a 2-sided 1 sample test of the mean of blood pressure or cholesterol level, whatever, in our target population compared to some value that is known from a whole population. So in cases where we did have 2 samples, so where we're estimating the mean of smoking males and of non-smoking males from samples, we don't have the truth for one of them, then your null and alternative hypothesis look more like this. So there's no values in here because we don't have the truth, we don't have that 211. Our hypothesis is just going to be that those 2 means are the same, our null hypothesis. So there's no numbers in these hypotheses now. You want to give an example of a 2 sample test? I just gave one. How about a null hypothesis that students in ComHE programs have same income as students from environmental and occupational health and safety. We don't have the value from the entire population of those 2 different types of students. We're going to do a 2 sample test. We're going to have to sample from both of them. We're going to have to estimate the mean incomes for both of those groups, and based on how different they are accept or reject the null hypothesis that they're the same. Or, of course, the malaria example is an example of a two-sample hypothesis test. Yes?
So for this one, then we need to do the calculation in order to find the mean.
So you need to do the calculations to find the mean. Yes, I mean, in the one-sample test, you're estimating one mean. In the two-sample test, you're estimating two means. In the one-sample test, you have one estimated mean, one known mean. In the two-sample test, they're both estimated. Yes? Yeah. Oh, wait a minute. Could I? That should be not equal to 0. And under the null hypothesis, it would be that they're equal to 0. Those are equivalent ways of writing the null and alternative hypothesis. Do you have a question as well?
Would let's say in the previous example, checking to see among men who smoke.
Mm-hmm. The previous example among the men who smoke.
Now, if we said we wanted to take that, we take samples from men who smoke, blood pressure from men who smoke, and from women who smoke.
So if we were going to take a sample of smoking men and a sample of smoking women, then that would be a two-sample test. Yeah. Yeah, the key is that with both of them, then we're estimating a mean from a sample that we're taking. So we have sampling variation described by a sampling distribution for both of those samples. Yeah, good. The hypotheses look very similar for if it's a proportion, mean or proportion. The tests are pretty similar as well. So in the malaria example, one of the null hypotheses was that the prevalence of anemia is the same in the control population as in a population that is receiving the malaria screening and treatment. And alternative hypothesis is that those prevalences of anemia differ. So we've been discussing 1 and 2 sample tests. And just to make things confusing now, unfortunately, there's also 1 and 2-sided alternatives. So those previous couple slides, those were 2-sided alternatives because the alternative hypothesis was just that the means or the proportions were different. So that could be more or it could be less. Those are the 2 sides. In a one-sided test, then you actually have an explicit hypothesis about which it is, that the mean in your population of interest is greater than in the null population, or it is less than in the null population, but not the other way. So you can recognize a one-sided hypothesis test by the way the null and the alternative hypotheses are written. And the null hypotheses, it still has to contain no difference. So here it's less than or equal to. And the alternative is just that the mean in our target population is greater than in the null population. Yes?
why are we still giving it the less than as well? You know, when we give it the null, it's not really changing. We say there's a possibility that if we go, it's either be equal to or it could be one less or two less. It's still a change or a difference.
Yeah. So there, in this case, under the null hypothesis, you're allowing that there still could be a difference in that the mean could be the same or it could be less than the null mean. And the way you can think of this, I think, is that your null hypothesis is that our mean is no greater than this value. So, and your alternative is that it is greater. So it's still a kind of a no difference, except that it's not greater. Yes. The opposite of greater is. Yeah, that's a good point. So a useful way to think about this is that to think of your alternative hypothesis first, that the mean in your target population is greater than in the null population. And then the null hypothesis then is what's remaining, which is that it's not greater, or in other words, it's equal to or less than. Two or one-sided alternatives, these are also called one-tailed tests, are actually very rarely used. You need to know what they are, but we don't generally use them. And in fact, a lot of journals strongly discourage their use, and I'll tell you why. But your decision to use a one-tailed or a one-sided alternative must be very well justified, and not just because you think that it should be that way, but a better justification than that. A common reason for, justifiable reason for using a one-tailed hypothesis would be if instead of wanting to know whether a drug is effective, you only want to know if it isn't harmful. So you don't care whether it's effective or ineffective as long as it's not harmful. That is a case where you might choose a one-tailed test. But if your clinical trial were to determine whether a drug is effective, you don't know in advance that it's impossible that it could be harmful. So you can't choose a one-tailed test or a one-sided test, if that makes sense. So, and it is somewhat controversial because the one-tailed test will give you smaller p-values, because on your sampling distribution you're only looking at one of the tails. And generally you'll get a p-value that's half the size of the two-tailed test. Yes? So what does a one-tailed drug trial look like? This could be a case where trying to think of an actual no harm drug trial. I can't think of one off the top of my head, but if it were one where, say, you were testing a generic drug, a generic alternative, compared to an existing drug, where there is really no plausible way that it could be better than the existing drug, and all you wanted to do is test against the alternative hypothesis that it's worse, you might choose a one-tailed test. And also, that would make it easier for you to accept that alternative hypothesis that your generic drug is worse. So it's not. So rejecting the null hypothesis is maybe a good thing then if it is saving people from being harmed by the drug. So I think there are some other examples too. Maybe I'll try to find some other examples, or maybe I'll put all of you on the assignment to try and find a published example of someone who used a one-tailed hypothesis test, and then we'll discuss them in a future class and see whether we think they're justified. They're rare. There are not too many examples where people use one-tailed hypothesis tests. They're rare, but you have to know what they are, and if you see a paper that's used one, to decide whether you think it was a good decision or not. And this is the key aspects. This third point here is that it must be clearly justified in advance of doing the test. So before you do the test, you must decide if you're doing a one-sided test, and there must be really no reasonable possibility of another alternative hypothesis. It has to be very clear that that is the appropriate alternative hypothesis to use. Okay, on to step 2, which is select a significance level, the value of alpha, which is that type 1 error probability. So it's the probability of rejecting your null hypothesis when the null hypothesis is true and you've only rejected it because of random sampling variation. It's usually taken to be 0.05, maybe 0.01, some small value. Step 3 is going to be to calculate a test statistic. In the examples we're going to do now with one sample z-test, it's going to be the z-score, the z-statistic, whether it's a probability or a proportion or a mean. And the important thing about that statistic is that it's something that we know what the distribution would be under the null hypothesis. So we know that that if we have a normal distribution and we subtract the mean and divide by the standard deviation, we know that it's this standard normal distribution, and we can look up probabilities in the appendix of our book. So the test statistic is always something where under a null hypothesis, we can look up the probability of getting any particular interval of values. So the test statistic is going to be, for the time being, based on the normal distribution, and then the p-value, which I'll get to on the next page, is going to be an area under the tails. Quick question: in this picture, if this is our type 1 error, would this be a one-tailed or a two-tailed hypothesis test? What's that? One-tailed, that's right. But we're two-tailed, we would be looking at area under both tails. And then step 4 is to actually calculate a p-value, which you can do by looking up probabilities from, for now, your normal distribution table. And the p-value is going to be your probability of getting the test statistic that you got or something more extreme than that. So, and by more extreme, I mean that if you have a positive value, getting a larger value than that, or getting something smaller than the negative of the statistic that you got, that being a two-tailed test. So for now, it'll be the normal distribution, but all hypothesis tests follow this same basic procedure of calculating the test statistic and then calculating the probability of that or something more extreme under the null distribution, the null sampling distribution. Then finally, step 5 is to either accept or reject, your null hypothesis, and to make conclusions and write that down in the language of your study in a way that's relevant to the audience of those results. All right, so maybe we'll go through this, and then I wanted to kind of go through these steps for the malaria study, at least qualitatively, not actually calculating the test statistic, but talking about what all of them are here. So what is the outcome variable? I mentioned that before. There were 4 of them. There was anemia at 12 and 24 months, prevalence, and there was spelling scores and arithmetic scores, different times. So let's just take one of them, the arithmetic scores at 24 months. What are H0 and HA here? First in words. Yep. Yep, so H0 is that the arithmetic scores at 24 months are the same for those who are screened and treated for malaria as for those who are not. And by saying that they're the same, I'm talking about the populations, not just the individuals who happen to be in the samples that we're observing, but we assume that those samples are representative of an entire population. And the alternative hypothesis is that they're not the same. So they're either more or less. I mean, of course, the researchers probably thought here that the arithmetic scores would be higher, but they didn't do a two-sided or a two-tailed, or they didn't do a one-tailed or one-sided test because, you know, they can't rule out the possibility that maybe all of the time spent on the screening and something about the treatment could actually lower the scores. It's not an impossible thing, so you can't justify doing a one-tailed test here. What's the significance level alpha here? Can we tell anywhere? Let's see. Here's a clue. It's a 95% confidence interval. They don't actually give any p-values here, but because they're giving a 95% confidence interval and the equivalence between confidence intervals and hypothesis tests, they're using an alpha value of 0.05. And with a risk ratio, the null hypothesis would be that that risk ratio is 1. That there's no difference, or there's no, the ratio of of risks, this is for anemia, is the same in the two groups, or that the prevalence of anemia is the same, so the ratio is 1. What is the p-value? Oh, they do give some p-values here. Here's a p-value. Here's a p-value. So they give p-values for these prevalence tests. They don't give p-values for the educational outcomes. But we can tell both from the confidence intervals that include 1 and from the p-values that are greater than 0.05 that they did not reject H0. And how did they report these? Well, they say, so this is that step 5 where you put it in the language of the study, no impact of the malaria intervention, screening and treatment, or IST intervention, or intermittent screening and treatment, was observed for prevalence of anemia or on prevalence of P. falciparum infection or scores of classroom attention. So those are the statements of their null hypotheses, and it's stated in that they did not reject the null hypothesis. But an apparent negative effect was seen on spelling scores in the younger class. So it's kind of justifies that, you know, that you wouldn't choose a one-tailed hypothesis, because for some reason apparently all this time spent on screening has kept students from practicing their arithmetic, I guess. Any comments about that study? So you don't have to know how to analyze a cluster randomized trial here, but you can still interpret their results. Yeah. Right. Okay, yeah, conceptual understanding of p-value. Let's go back to this, and I'm going to add another tail on here. So you remember from our class on the central limit theorem, you learned how to draw and how to write the mean and standard error of a sampling distribution. That is, the distribution of means that you would get if you repeatedly kept on taking samples. If you were to keep on repeating your study and calculate your mean or your proportion or prevalence every time, you learned how to calculate what the distribution of those sample means would be. Now, you use that to estimate a confidence interval, right? You took the mean of the sample as your point estimate for the population, and you put a confidence interval at plus or minus the margin of error. Now, when we're doing the hypothesis testing, we go about it a little bit differently. We take the null hypothesis, and under the null hypothesis, we calculate a sampling distribution for samples of our given size. We add the margin of error plus or minus the null value to calculate the probability of getting any particular or range of samples. So for a hypothesis, for the hypothesis test, where we have a hypothesized mean like that 211 milligrams per 100 ml, that is going to correspond to a z-score of 0. That's the population mean. And under the null hypothesis, the mean of our population of interest will be equal to the null value and correspond to a z-score of 0. And then the variability in sample means under the null hypothesis will be given by the standard error. So you know then the mean and the standard error under the null hypothesis. And for any given sample that we take, we can calculate the z-score using the difference in means and the standard error, because it's a sampling distribution, and then calculate the probability of getting a z-score that is either greater than what we observed or less than the negative of what we observed, and that is the p-value. So it is, if you were to keep on doing your experiments, it's the fraction of times that you would get a mean or a proportion more extreme than what you got. So if you have some fairly extreme value and you calculate that if the null hypothesis is true, you're only going to see that happen 2% of the time, then you have a p-value of 0.02. Right. So if you have a p-value of 0.8, something high, that means that 80% of the time, if you do 100 studies, 80 times, you know, even if the null hypothesis is true, 80 times you'll get a mean that is as different or more different from the null hypothesis, the null value of what you saw. So it means that your study is really quite consistent with the null hypothesis. It's when you get, you know, a handful of beans that would very rarely come from this bag that you're going to reject the null hypothesis that it came from that bag. Yeah.
So how the value of p further right to that?
So a small value of p is going to be, say, this. So if you got like z equals, let's say, 5, that's going to be a small p-value. If you have, say, z equals 1, so your mean is not very different from the null value, that's going to be a large p-value. And if you happen to get a z that is almost identical to, you get a z of very close to 0, so your mean is very close to the population mean under the null hypothesis, then you're going to have a p-value of almost 1, because it'll be the whole area on both sides of this curve. Does that help? Yeah? Yeah, so, okay, so let's suppose the example of the cholesterol levels where the mean is 210, standard deviation is, I don't know, 10 or something like that. Then if we take a sample size of 100, the standard error is going to be 10 over square root of 100, which is 1. So that means the standard error, so then the sampling distribution will be centered around 210, and it'll have a standard error of 1. So if we take a sample of size 100 and we get a value of 211, that's a z-score of 1, right? So if we put z equals 1 on here, does anyone remember how much error is inside z is plus or minus 1? Yeah, it's 68 inside, 34 outside. So what's the p-value? .34. Yeah, so in that case, with a population mean of 210, a standard error of 1, if our sample of n equals 100, we observe a mean of 211, so z-score of 1, our p-value is going to be 0.34 on a two-sided alternative. Yes? Because it's only 0.17 under the right tail, 0.17 under the left tail. The total probability of having z greater than 1 or z less than minus 1, that's the p-value. Because 0.68 is the area in the middle. Yeah, 0.32 is the area in the two tails. 0.32, and it's p over 2, 0.16 in the right tail, 0.16 in the left tail. Whereas if we, from our sample, got a mean of 213, so a z-score of 3, what's our p-value going to be? Yeah. Didn't remember that part of the empirical rule? What's that? Yeah, I think it was, so it's 2.5% outside of 2, and I think it's maybe 0.3% outside of z-score of 3. So the p-value is going to be 0.003. We get a z-score of 3. So the further away your sample mean is from the null hypothesis, the lower the probability under that normal distribution and the smaller your p-value. Right? It's the probability that your sample came from that null distribution. That's why a small value means you reject the null hypothesis. I'm way over time, so I'm going to skip the examples. Here's a full example of cholesterol. We have a couple examples, a one-sided and two-sided. Take a look at these. If you have questions about them, post them on the Google group. It's a good example to go through. Know the difference between a one-tailed and a two-tailed, or synonymously one-sided and two-sided test, also a one-sample and a two-sample test. And we'll get to power after. Don't worry about power for now or for the exam. I'll do this when we come back. Yes. It's focusing only on the stuff since the last test. I mean, I probably can't completely avoid the stuff before just because, you know, the stuff we are doing since then still depends on it, but it's going to focus on the stuff since the first exam. And this will be your last exam. After this, no more exams. You'll have a final project. The final project is nice, it's fun. You'll enjoy it. Yes, yes, I will post ASAP. I should be able to do it by tomorrow. I'll give you some practice questions and same rules, same everything for the exam. All right, thank you.